Have you ever wondered why merge lanes are a certain length on different roads? Engineers have to calculate how long it takes for vehicles to accelerate up to speed to know how long to build them. In this lesson, we're going to be talking about using graphs to calculate displacement during accelerated motion. So, when we looked at displacement time graphs, there are three different shapes depending on the type of motion. We had no motion, where an object was stopped, uniform motion, where the line went up at a constant rate, and accelerated motion with a curved line changing as that object changes its velocity. Then the slope of those position time graphs can give us the speed of the object. But we can't actually calculate the slope of a curved line, so we transfer this information to a velocity time graph. So in a velocity time graph, if we have no motion, the object is stopped. There's actually a line there at 0 for the velocity. If we have a uniform motion graph, the velocity stays constant as time on the x-axis changes. And if we have an accelerated motion graph, we have an acceleration that increases, and it's shown through the velocity changing as the time is changing. And this is a straight angled line, and it's similar to how the uniform motion on a position time graph looks because the trend is the same. So I want you to take a quick look at the axes here because one is a position time and one is a velocity time. So they look different, but they're going to give us different information. But they still don't demonstrate a uniform trend or a straight line. So we can calculate the slope of the line, which is rise over run. So the change in velocity divided by the change in time. If we already have a formula that looks at the change in velocity over the change in time. So this is final velocity minus initial velocity divided by the change in time. And this one's from our data booklet. The slope of velocity time graph gives us the acceleration of the object. And the other piece of information that we can find from a velocity time graph is displacement. So just like with the speed time graph, this is done by finding the area under the line. But this is not a rectangle. This one's going a triangle shape. So if a car left home from point A and traveled 10 meters per second to a store a few blocks away, the trip took 45 seconds. How far away is the store from home? So here is our velocity time graph scenario. So point A, point B, 10 meters per second for 45 seconds. So we're going to draw a vertical line up from 45 seconds and shade in the area under the motion line. And we're going to find the area of the shaded region, which is a rectangle. So we're going to go base times height, which is 45 seconds times 10 meters per second. So we get 450 meters away, which is how far away the store is from the home. Now, that was easy because it's dealing with uniform motion, so the area is a rectangle. But if the object's accelerating, we have a triangular area. So we're going to go length times width divided by 2. So for example 2, an athlete is going to train by starting from rest and steadily increasing his speed. So after about 2 minutes or 120 seconds, he'll be moving at 6 meters per second. So we're going to sketch a velocity time graph and use it to calculate his acceleration after a minute. So the first step is going to be to draw a graph and plot the 2 points on the line and shade the area beneath the graph. So we're starting from rest. Therefore, we're going to start from the axis 0, 0 and put another point in there at 120 seconds and 6 meters per second. Then at 60 seconds, we're going to draw in the area under the graph. We're going to use the slope to calculate acceleration. So we're going to take 3 meters per second at the y-axis and 0 meters per second at our origin and divide it by 60 minus 0. And this gives us a total acceleration of 0.05 meters per second squared. Now we can calculate the area under the graph to calculate the distance traveled. So we're going to go length times width divided by 2. So we have 60 seconds multiplied by 3 meters per second, and then divided by 2 gives us a total distance of 90 meters. Now we can use velocity time graphs for objects not starting at rest. So far we've looked at all the objects that started at rest. but that just means that they start at the corner of the two axes, 0, 0. But an object can be traveling from one speed and accelerate to another. So these graphs, the line's not going to start. It will start on the y-axis, but not 0 on the x. So a car turns off of a residential street with a speed limit of 60 kilometers an hour to a highway with a speed limit of 110 kilometers an hour, or 31 meters per second. Well, in the merge lane, it takes the driver 12 seconds to accelerate to highway speed. So we're going to draw a line and find the acceleration, and then find the distance traveled. So we're going to plot those 2 points on the graph. First, our velocity was 17 meters per second, and second, at 12 seconds, our velocity was 31 meters per second. Draw a line between these 2 points, and shade the area under the graph. So we're going to use the slope to calculate acceleration. So rise is going to be 31 minus 17 meters per second divided by 12 seconds gives us a total acceleration of 1.2 meters per second. Now we're going to look at the area under the lines to calculate the distance traveled. So area 1 is going to be base times height, which is 12 seconds times 17 seconds, or 204 meters. And area 2 is 12 seconds times 14 meters per second divided by 2 at 84 meters. So the total distance traveled, once we add them together, is 288 meters using significant digits. This is going to be 2.9 times 10 to the 2 meters. So that's how far the driver traveled in the merge lane.